All right, so I've done it. I've created a model of the flat Earth and the globe Earth in Blender 3D. So we can look at this and see what it would actually look like if you were from the perspective of either model. And so I'm going to flip over here and we can take a look at this. Okay, so we are going to look at this and I'm going to go ahead and play it. So we've got the flat Earth plays like a time lapse of a day, so to speak, and then the globe will play. Um, Now, I have the other disappear so that it's not distracting when you're looking at one model or the other. But essentially, you can see that I've tried to replicate both as closely as possible. Obviously, I'm dealing with some limitations with Blender. Um, the way that the sky is built, it is actually an object. So Blender has a way to do a sun lamp, which would have worked a little bit more accurately to what the sun would do, but because that sky object is in the way, we can't do that. So what I did is I created a light that is essentially acting as a spotlight, and then a object, which is the sun and the moon, and same thing for the flat Earth model here. Now with this one, the sky, um, well, with both of them, the sky is rotating. So the sky um, is basically downloaded right from the internet. You can easily find, so both the sky and the terrain for both models are easily accessible online. I basically just took an image and wrapped it around that object. There's a tutorial that shows you how to do this. It's pretty straightforward, um, that I will link to in the description here. And so I'm going to go ahead and pause this. And so what I've done is essentially, now I'll try and make this available for anyone to see, but and download and kind of play with. So on both surfaces, I have populating these little buildings. I'm going to try to zoom in on one. The scale of this is not proportional. So unfortunately, in Blender, I mean, you're dealing with meters. You can switch it to kilometers and that kind of thing, but then you're dealing with the distance at which you can render things, which can be extended out. But things get kind of crazy the larger that you make them in the world space. So we're just kind of doing a proportional, they're proportionate to each other, but not like the in-world distances won't exactly make sense. So what I've done is created these guide markers. So these big ones here. Now, for the sun, I stacked up three of these. So in the flat Earth model, it is said that the sun is approximately 3,000 miles above the Earth. So each one of these, um, there's three of them that are kind of joined here, but each one of these is 1,000. And so the tenth of that would be, um, I'm sorry, yeah, a tenth of that would be 100 miles. And so within that, we have 10-mile squares. And then within that, I broke it down even further. So on each of these buildings, I believe these are 1 mile. Okay, so I have the universal one here right at the world origin in the middle here. So Obviously, the large square, like I said, is 100 miles, and the small squares are going to be 10 miles, and the whole thing is 1,000. Universal reference. So these, okay, so the thing extending from these buildings, and this is what the buildings look like. When you zoom into them onto the Earth, it's basically a skyscraper. That's what I was aiming for. It may not be exactly the size, like this would be a building, this would be like a person. I don't know. That's not exactly to scale, but it's kind of giving you some reference here. So this is going to be okay. I did this like a week or two ago, so I'm just coming back to it. Um, a mile is roughly 5,000 plus feet. So that's why they're broken up into five. So you get roughly 1,000 feet per section. And so this one is broken up into 10. So apologize for using imperial measurements here, but you can convert it to meters and kilometers if you want to. Um, so yeah, again, each of these small squares is going to be roughly 100 feet. A skyscraper is estimated to be between 400 or something and 2,000 feet. So this one is one, two, three. It's shorter than an average skyscraper, but yeah. So a note on the sun again, it's not going to be quite precise because the actual sun is larger than the Earth. So if you think about it in its distance, all of the light coming from the sun is traveling in the same direction when it hits the Earth. As far as the sun is concerned, it's radiating in all directions. But as far as the Earth is concerned, it's such a minute section of that total light that's being emitted that it's essentially like perfectly straight. Whereas this, because it's a spotlight, is radiating out from a single point. Um, so if you know Blender well enough, just hide the sky, add a sunlight, but then it won't be parented to the control. Let me find the right controls here. So sky control. So if I hit R and Z, I can rotate it around this axis, and that's like as if time is passing. Now the sun, okay, so it's reversed. The idea kind of relativity, where it's like it's based on your perspective. So if you were on this ball, this is what it would look like. It's the exact same as if the universe were rotating around the Earth. There's no difference. Um, so if you want to say the Earth is immovable, you could make an argument for that from the globe model, even. Although I don't think that's what it's talking about. It's talking about the Earth, like what you stand on. It's solid. Like when you walk on it, it doesn't move. Like that's what it's talking about. That's the only thing that they had in mind when they were writing or reading that. So but that's neither here nor there. We're here to talk about the models here in Blender. So done rotating that for now. If we go back to the flat Earth model, we have the sky control rotate on Z and boom. So another thing, it's like, why is it like this, right? Well, why is the light like not round? Because that's the way that they portray it. Any flat Earth like diagram model that you see online, that's the way it has to be because the sun illuminates, roughly half of the Earth. Whereas if this was a spotlight that wasn't like stretched out, so I had to stretch it on one axis. So, this is kind of the way that it initially comes, but, I had to fix that. And so that's one thing to think about, I guess. There is this: why is the light projecting in this shaped manner? Um, but, if we control the sky, this is the way that the sky would move as well. So we're told that the stars are in this firmament, this dome. okay, and according to the flat earthers, like the stars are moving around inside the dome. And the south, right? So we don't have a south pole, we have the south as the outside border of the earth, right? And there is an ice wall here that you would run into uh, this ice here. And then somewhere beyond that is the firmament, which extends upward in a dome shape. It's a little bit of a squashed dome, uh, but that's usually how it's portrayed online. So that's what I went with. And you have the Earth, you have the Sun, you have the Moon at their respective height. Now we can get into what it would look like from each place. So if I click this button, I will view that camera. Okay, and so we're starting on the flat Earth side. And if I hit play here, it's going to give me 1 day of like motion of the heavenly bodies. And then it'll flip me over to the globe and show me exactly what it would look like on that model. So what this is, where are we on the Earth? Good question. So we are basically the tip of Africa. And that's the same on both. So camera, leave the camera. This is where the camera is. There's Africa. We're upside down right now. But we are on the tip of Africa, and camera is directed south. So we're looking at the southern sky from basically the tip of Africa. And this camera is really, really small. So if you need to find it, do it from outliner up here, click on it. Period on the number pad will snap you to that object. Now, the camera on the globe is it's pretty high, actually. So this is actually in favor of observing curvature. So if curvature were to be visible, it would accentuate that. We're not trying to hide a lack of curvature here. But the reason that it's so high up is because if I do camera view here, the camera isn't actually that size. So if I grab it and I bring it too low, if I bring it down, so it's still above the earth. But if I go to camera view, I'm starting to intersect. And that's just kind of that's a limitation of Blender. I didn't want to make things too huge because things, like I said, start to go a little weird. So I'm going to undo that. We are roughly, I would say these are miles. So like a mile and a half above the earth. So that's within nominal ranges for like altitude, or maybe in a plane, whatever. But these are heights that you would be able to see as a human being. Uh, and so if we are looking south again at the sky, so if I play this from here, we will see that rotate and you get this pattern. Whereas if we were viewing from the flat Earth, now if you're in this file, it's going to hop you to that camera. So we have camera for the flat Earth starting at frame 1. The camera for the round Earth is starting at frame 125. During this period of time, both models are visible, and then it says, when they go invisible, if that makes sense. But that's only if you're looking at this file in the future. So we're back on the flat Earth, same position, the south of Africa, looking south at the sky. This is what it would look like from the flat Earth. Now, we can do this, right? You can go to the southern tip of Africa and point a camera at the sky. Which one do you think that it looks like? Well, somebody's done that for us. Okay, so this is a video available on YouTube called South Celestial Pole Full Night Time Lapse 8K. I don't know where this is from. Uh, New Zealand. Okay, so you can see this from Australia, New Zealand, Africa, southern tip of South America, So we're going to go ahead and play this. And which one does that look like? Okay, so you have a rotation point. It is called the South Celestial Pole, where roughly in this area, it looks like you have a point at which everything rotates around. Now, this is a time lapse. We can go ahead and speed it up because mine is very fast. This is very slow. Okay. All right. And so if we go back to, apologize if you can hear my kids running around upstairs. But if we go back to this, go ahead and play that. This is the flat Earth. So everything is kind of zooming around. There's no rotation point because the only rotation point that we should be able to see from this sky is in the North Pole, which is up this way, which we should also be able to see. We should be able to see the entire night sky at all times. So that's one thing to think about. Now, there are reasons that have been provided why that might not be the case, but it usually has to do with some extreme levels of refraction and some properties of this dome of the sky that we aren't aware of. And it's frankly um, very difficult to conceive. Um, so again, we don't have to lock ourselves to the camera. I'm just going to point this straight up. Again, we are seeing basically the entirety of a day within like 2 seconds. So it's going very fast. But so in the north, we have a celestial pole, which is the same in a globe Earth. And that we have this in the flat Earth, but we do not have a south celestial pole. Whereas if we hop over to the globe model, that is exactly what we see. So the camera view is rather small, but if you were a person, you would see more like what the entire viewport is here, which is essentially the same as what was in that YouTube video. All right. Now those stars are much fainter and are marked for, you know, obviously you have like these regions marked out and like the names and everything, but that's essentially what we're seeing. So that's one thing to think about. Now, let's point the camera somewhere else. So again, if you're in this file, what you can do is take the camera control. I recommend doing this rather than moving the camera itself. This is going to be parented to the exact center. So you can take this and rotate it any which way. Center dot ball, sorry. So the camera control is going to give you the ability to kind of change the direction of the camera. Center dot ball will give you the ability to move the position of the camera on the globe. So I'm going to advance this to timelapse day over here. Sorry about that. So we are somewhere here in the Middle East, like kind of north. I don't know if this is like Syria or this. I have no idea. Um, and I'm in free rotate, so that's hitting R twice. And we're gonna hopefully be able to see like a sunset. Okay, so that's kind of what we see, right? So um, you can bring it all the way back around, and then starting there again. That's kind of what a sunset would look like on the globe Earth. Ew. Okay. And so kind of ignore this boundary of the camera. Your eyesight would be much closer to the entire viewport. All right, so now we can move this camera here. Now this map is a lot easier to navigate your camera on. Well, we don't even really see the sun. It's so high up. We're still looking south. There's the sun. There it comes. There it goes. This is what the sun coming and going would look like on a flat Earth if it was 3,000 miles in the air. It never even touches the horizon. And this is to scale. So like um, the United States is roughly, where's that guy that? Yeah. So let's try to keep this level here and put it roughly there. Okay, so this is just to show that this is approximately 3,000 miles. The United States is about 2,800 miles from east to west. Yeah, so this is diagonal right now. If we straighten this out, that's, you know, roughly 28. Then you got these two here of the remaining 30. So that's, or 3,000. 3,000. Um, so if we fix this back up here, 90 straight, boom, rotate the sun, and you can see that it's approximately the same. So this is to scale. Like this is what the flat Earth model is. So roughly, okay, Google says between zero, which seems between 0 and 4,000 miles. So I went 3,000. I think that's what the Flat Earth Society website is. Some people say that's a fake site. Flat Earthers say this is people trying to mock Flat Earth. But of all of the models that I've found, it's not going to get any closer because the closer that you get, you run into other issues because there would be parallax. There would be more parallax between the sun and the sky. Um, so what that means is, like, if I look up, if you look directly up, like this is what you would see from one place on the Earth. This is the moon. It doesn't matter, moon or sun. So you like, let's just leave it at frame 47. So if I was over here, I mean, the sun is way less parallax than the moon should have because it's further away, but I mean, it's still, moon's pretty far. So, um, let's just put something here so I can rotate around it. Just, I don't know, the cylinder. All right, we're on this cylinder here. Just go next to it. Okay, now if I look at the sun, you have like Sagitta, whatever star that is, that there would be like roughly behind it. Obviously, it's daytime, but you can still see stars behind the sun with technology. So that's Sagitta, and we're in where are we? We're some Scandinavian country up here. Now let's snap this to the surface and Okay, and then I'm just gonna like move the camera to it, move outside of the cylinder, look up, and we've got Corona Borealis and like Boots is nearby. So we've completely changed the direction at which we are looking at the sun as it relates to the stars. So like you can see. So if I drag the camera from like one part of the earth to the other part, you get this parallax effect where the background stars are shifting in relationship to the sun. This is precisely what you would see if the sun was roughly, 0 to 4,000 miles. It's 3,000, but this is what you would see. You would see as like from different places on the earth, you would see a parallax effect. You wouldn't see this because you can't travel this fast, but you can, communicate with people in various parts of the earth and say like okay, you know, particularly the moon, because you can actually see the stars, but it's essentially the same effect. If it was 3,000 miles up, it's really hard to say things about flat Earth without making it sound like I'm just ripping on it. Like I'm trying to be measured here, but like if I was in this part of the United States, you know, like Midwest area, and I looked up, I would see these stars, whereas if I was, way over here, let's say, um, get out of the way, I would see these stars. So you can back up the video and see what stars we had just seen. This is not the same part of the sky at all. This is what it would look like if the moon were 3,000 miles in the air. So we switch over to the globe, hop over to the camera. Um, this is not accurate, right? I can't replicate it with the sky being visible, but like imagine this sun. So get rid of the sky. Like imagine this sun. I don't actually know what's happening right now. So I created a sky, which is not the real sky, but it's a world shader. So it's actually like, infinitely distant from the actual objects here. And let's take this sun and just move that. Okay, that's still like way, way closer than it actually is, but doesn't matter. It's good enough. So let's play. Right. So we've got flipping off on the camera. So we should actually be able to see that now. And it's a little bit closer to what things would actually be like. So I'm gonna grab the camera, just make sure that I'm like, because I don't really want to look through that camera, but we're next to it. So like, I'm like, why doesn't the sun go down at an angle like that? Well, it kind of does. You just don't really see it, um, unless it's like summer, um, and you're in like the like a central-ish part of the planet. It's the same in the flat Earth, I guess. If you're further north or south, the sun's going to move in different ways in relation to you. So this is our kind of our day. All right, so we've got our camera on the Earth, and we're going to look at it going by. So we've got these stars here. Now, if I go somewhere totally different and we'll just like watch the sun to see where the stars are. Just like keep your eye on it. And it doesn't really matter, although, it's still really, really close compared to the actual sun, but you can see that there's way less parallax than what we saw on the flat Earth. And in reality, this is like, you know, even further away. You have virtually no parallax. Now the moon is closer, but it's still very far away. I'm going to shift that this way, and I have to move these things back, but um, you see that, right? It's like almost it's like it's some, but it's not nearly as much as you would see on a flat Earth. So there are some problems there. So this is the file that you will get if you download it. Now, those are the major glaring issues that I find with the flat Earth, and frankly, yet to receive any reasonable answers to those problems. And those are observable, they're measurable, as I've demonstrated. Um, I don't know any way around that other than saying like magic is happening between your eyeballs and the sun and moon and stars. Like some like shifting of the light. It's like just bending it in these strange ways. In one way, it's bending it this way. You look another way, it's bending it that way. It's just, I mean, I don't have another way to put that. Like these are the problems that I see. So if we, and then, so another one for me is Australia. That's why I'm looking at it. Why is it so absurdly long? And like everything is stretched out. The further south you go, it's like, look, this is a tip. Why is it so wide? Why is the tip of Africa so wide compared to the top of it? Like this is measurable, right? Like especially Australia. Everything is like skewed along. It's because it's stretched. You're stretching a map which reduces down to a point on one out to the entire perimeter on the other. So you get this strange skewing all on the outside. So if we go inside here and like measure, it's like well over, this is 3. And then if we rotate it, it's like 1,000, 1.5, maybe in like some places. So, so this is something measurable, right? You can go on Google Earth or Google Maps and plot, a drive from the east to the west of Australia. That's going to take you a certain amount of time. Then you can plot a drive from the south to the north. That will take you a certain amount of time. So you would expect if this was the shape of Australia, that they would be wildly different times. Like it would take you way longer to travel east-west than it would north-south. These are facts. Okay. How long does it take? Google Maps. But look how Australia is actually shaped. Like this is the shape of Australia. So let's plot some directions. Why don't I have like towns? What is going on? Directions. Oh, because I'm in stupid Bing. That's why. Unbelievable. Good. Come on, Bing. Get with the freaking program. Up here. So like this is 36,000 kilometers. We go from Brisbane to somewhere way over here, let's say. Is there any more straight route? Let's just say there, because that's way closer to what it actually would be. 4,277. So that's 45 hours. It's like these are like roughly the same amount of time. Compare this distance and this distance on a globe, and then compare this distance and this distance on a flat Earth map. Now, you could say, well, the shape of Australia might not be exactly correct in this, you know, flat Earth representation. But then you have a problem of longitudinal lines that cross through Australia, right? So if we pull up a map or a globe, anyway, there's a line there. You just can't really see it. Okay. So point being, like these lines are this way, and these latitude lines are this way. And like, so like, if you stretch out your map, like that is the shape of Australia that you would get. The one that I was showing you, flat Earth map with and yeah, so it's like roughly the same number here and here because you have to do that. You can't just say, well, on our map, the longitudinal lines are, it's only passing through like two. And it, the same number of latitude lines. It doesn't work like that. Like you have to be consistent. And, look, you have a super wide tip. So South Africa, it has this shape to it. Like it's, again, you can measure like travel times. Okay, this isn't something that you can fudge. But if you go here, it's like it doesn't go down to a point. It's stretched out. So like these travel distances should be exactly the same from like here to here to here to here. But they aren't because that's not how it is. So again, show me something observable that actually demonstrates that the Earth is flat, and I'll believe you.